Hi everybody, this is lecture 11 and today I will tell you about, I'll finish telling you about the gradient vector and then I'll move on to two new topics, directional derivatives and vector fields. So the thing I'd like to tell you to wrap up last lecture 10's discussion is I want to explain to you a little bit more, tell you a little bit more about the theorem that we explored last time. And this theorem told us what the gradient vector is geometrically, how to interpret the gradient vector geometrically. So last time I gave you the 2D picture for the theorem, but the statement still makes sense in 3D, and the statement also remains true. So today I decided to illustrate this theorem for functions of 3 variables rather than 2. Okay, here's what the theorem says. It says that if you look at a function and you compute the gradient of the function at a particular point, maybe this point here, x0, y0, z0, then you're going to get a vector. And the theorem is telling us that this vector, the gradient, is perpendicular to the level set of the function at that point, right? So at this point, f is going to have some value. Let's call it c, and then I look at all other values, all other points x, y, z in three-dimensional space, where f takes that same value, where f is also equal to c, right? This gives me a level set. So in 3D, it gives me a level surface. In 2D, it would in general give me a curve. And the theorem is saying that the gradient vector is perpendicular to this level curve. Let's see that happen. Let's see why that's true. So this discussion, the next 5 minutes of discussion, is not something I expect you guys to reproduce in an exam, but I think it's useful. It adds. I think it'll help you be more confident when using this theorem and help you use it correctly. Anyway, let's do it. So let's try to understand, let's try to prove the theorem. Well, first of all, I should before I can prove anything, the statement has to make complete sense. So I should really explain I should make a caveat explaining what the theorem is really saying. So what does it, right, the issue here is this perpendicular sign. What does it mean for a vector to be perpendicular to a possibly curved surface? And the answer is that when I say that the vector is perpendicular to the surface at a point of the surface, I really mean that the vector is perpendicular to the tangent plane of the surface at that point. So let me draw something here that looks like the tangent plane of the surface at that point. Okay, so there you have in blue the tangent plane. And what this means in turn is to say that that the gradient is perpendicular to the tangent plane. What that means is that the gradient is perpendicular to every single tangent vector and every single vector in this tangent plane. So if I give you a tangent vector v, so what we want to show is that if we start with any vector v that's tangent to the level set, then the gradient will be perpendicular to that vector, right? We want to show this perpendicularity over here between the gradient and any tangent vector. So let's start with any tangent vector. So let v be tangent. So it's a vector by the notation. You could tell it's a vector. Be tangent to. So let me give a name. So to the level surface, let me call the level surface S. So I'll do that. Introduce this notation on the picture over here. So S is my notation for this surface, this level surface. So let F be tangent to S at the point where I computed the gradient, x0, y0, z0. Okay, so we want to show that the gradient is perpendicular to v. So in algebraic terms, we want to show that the dot product between the gradient and v is equal to 0. So let's To do that, we're going to have to dig a little bit deeper. So what does it mean for V to be tangent to the surface? So by definition, the answer is that, so when I say that V is tangent to the surface, I really mean that there is some curve inside the surface. Here I'm drawing one, right? So there is a curve in the surface. So here I have a curve in the surface, and that V is the tangent, is really a tangent vector to a curve contained in the surface. So, so in practical terms, this means the following. So by definition, so V is the velocity vector of a curve contained on our surface. So by definition, V is the velocity vector of a curve inside our surface. So the curve will be described in terms of, it is really a sequence of points, right? A bunch of points. They all have x, y, and z coordinates, and I'll express these coordinates. So the sequence of points depends on the parameter. So by definition, V is the derivative at time 0 for some parametrized curve right, and this is a new term, a new idea. So for some parametrized curve, so this parametrized curve takes parameters t, so numbers t, to points in our surface. Okay, so what I'm saying is that if I have a so let's recap and put this all together. So we want to prove that the gradient is perpendicular to all tangent vectors to the surface at this point. Now, to say that f is tangent to the surface at a point is to say that there is some parametrized curve. Here I drew it in green. There is a curve inside my surface whose velocity vector at time 0 is equal to v. Okay, so now let's finish up the proof. So what this statement over here means, so to say that this curve, that all these points, x of t, y of t, z of t, so all the points in the curve, they belong to the surface, is to say that for any value of t, so any value of the parameter, the function, so s, so this point in the curve belongs to the surface. So this means, so now a point belongs to the surface exactly when f at that point is equal to c. So what this is saying is that f is equal to c. Okay? Now, so f is equal to, so for all values of t, the function is equal to c on this, on x, y, z of t. So as t changes, f of x comma y comma z of t does not change. It's always equal to c. So that's what we're going to use to wrap up our proof. So df, so df dt, so ddt, let me put it this way. So ddt of f of x of t, y of t, z of t is, on the one hand, it's 0 because f is constant and equal to c on that surface, and in particular on the curve, is equal to 0 on the one hand, and on the other hand, by the chain rule, so I'll just say here that I'm using the chain rule, it's equal to the x partial, so of f, times dx dt, plus the y partial of f times dy dt, plus the z partial of f times dz dt. Okay, now let's write this out. So this is all for t equal to 0, right? T is for t equal to 0. Kind of running out of room here. Okay. Now let's see what we have over here. So so the x, y, and z partials of f, they are just the gradient of vector when t is 0. So we should be looking at a curve which starts when t is 0, which starts at the point at the given point x0, y0, z0. So this is the gradient. So these three functions, these three partials are the components of the gradient, and here we're evaluating it at the point x0, y0, z0, and then we do the dot product with these three derivatives, time derivatives. So the three components of the velocity of the curve when time is 0, that is v. So you see, the conclusion is that 0 is equal to the dot product of the gradient with this arbitrary tangent vector on the surface. And so to say the two vectors, dot product of two vectors is 0 is the same as saying that vectors are perpendicular. So this wraps up our theorem. Oops, let me draw the square. So when we see a square like that at the end of the proof, we can be happy. So in summary, this is a kind of a complicated thing, and I crammed a lot of information together. But to summarize the proof, our goal, to prove the statement of the theorem, we have to show that the gradient of the function is perpendicular to every tangent vector in the surface, and then we have to use the definition of a tangent vector. So a tangent vector is the velocity vector of some curve inside the surface. Now, if a curve is inside the surface, the value of f does not change in this curve. And then this is stated here, that the value of f does not change in the curve. It's always equal to a constant. And then using the chain rule, we get that the rate of change in the value of f, that's 0, is equal to the gradient times v, dot product v. So this completes the proof. Okay, so let's move on to our next subject. This is directional derivatives. So let's discuss that. Okay, so let's say we start looking at a 2D situation. So if I have a function of two variables, I can do two things. I can take its x partial and its y partial. Oops, I want to write both here, not just y. Right, I can take two derivatives. And these two derivatives, let's recall what they're doing. So when I take the x partial, I fix the y variable. So I fix so this partial, if I evaluate it at a point, I get a number. This number, what is this telling me? It's telling me how fast f changes if I fix y at the y coordinate at that point, but let x change. So if I fix y and let x change. So if I move sideways to the right with speed 1, how fast does f change? And then the answer is this number over here. And so the direction for the x partial is the I direction, right? So recall this is just the vector 1, 0. Now the direction of the y partial is the j direction, right? Because the y partial is tells you what happens. So when we compute the y partial, we fix the x coordinate at a particular point. We fix the x coordinate of the point, and then we increase y with unit speed, and then we see how fast f is changing. Okay, so what I would like to explore with you now is what happens when f changes in a different direction. So in a direction other than these two. How fast does f change in that case? So what happens when f, if I move, when I move in a different direction? u hat. Okay, and here when I say direction, I really mean unit vector, so length 1 vector. Right. So what happens when if instead of going to the right or going up, what happens to f when I move in a different direction? That's what directional derivatives are going to tell us. Just a comment about our terminology. Normally a vector geometrically has two components, two parts to it. One is the direction of the vector, and the other is the length of the vector. But if I look at a unit vector, so if I know the length is 1, the only information that's left is the direction. So I use the term direction and unit vector as kind of as synonymous every now and then. So I think the book does too. So please be aware that sometimes the word direction means unit vector. But it's just if someone asks you for a direction in a homework or in the exam, you can just say in the direction of the vector 2, 1. That's not a unit vector, but it has a well-specified direction. Okay. So let's think about what happens. Let me draw. I wonder. Yeah, it's going to be worth moving to a different page. Okay, so let's see what happens then. So let me draw. Let me say I have we're in 2D, and then we have a function. So I'm going to draw the graph of the function. Like this. Right, so this is the graph, this is equation z equals f of xy. And I have a point x comma y, or maybe I should call it x0, y0, right? I'm fixing a point in the xy plane. And I want to know what happens. So, right, so f at that particular point, so the height of this, the height of the graph, of the point in the graph that lies over x0, y0 is f at that point. So this tells me, so this height over here is f of x0, y0. Now, what I'm going to do is I'm going to pick a direction, maybe this one here. I'll draw it thick. So I'm going to pick a direction. So u, and let me, actually for the purposes of my picture, I should draw it slightly less slanted. Maybe this will be good. So I'm picking a direction, and I want to know what happens what happens to f, to the function, when I move in this direction, right? So when I move in this line, what happens to f? What happens to the function? So if I move on this line, you guys can see. So I'm going to move kind of like this. So I'm just applying f to all values, all points on the line, and I'm going to get a curve like that. So one way to think about this is this red curve is the intersection of this graph with the vertical plane with slope given by u, right? I just take a line with slope u, so a line that contains x0, y0 and has the direction of u, so this gives me a line in the xy plane, and then just if I consider all points in xyz space whose first two coordinates lie on this line, I get a vertical plane. Okay, so, and then the intersection of this vertical plane with my graph just gives me this red curve. Right, so what we have, just a moment please. So what we have here, so we were asking ourselves what happens to the function when I move in this direction, in the direction of u. So in this picture, in this case, you see that the function would drop. The value of f would go down. So in this case, the derivative of f in the direction of that vector, whatever that means, should be a negative number. So now let me define that derivative. So here, let me just introduce some give names to things. So let's say that a and b are the coordinates of u, and then so definition of directional derivative: the derivative of f in the direction of u at the point x0, y0. So that's a new name, a new thing. This is, by definition, a derivative of an old sort that we already know. So it's, by definition, an ordinary derivative of a function of a single variable. So I'm going to give you a function of t and tell you to differentiate that function. And here's the function of t. It's just f of the starting point, x0. So what I want to do is just put in, let me just write the formula. x0 plus at, comma, y0 plus bt. And then I'll differentiate this when t is equal to 0. All right, so first let's see if this makes sense. So the derivative of the directional derivative of f in the direction of u. So the derivative of f in the direction of u at the point x0, y0 is a number. What number is this? Well, you take this function of a single variable t. So x0 and a are fixed, and then I have just one variable t inside in both inputs. I evaluate. So you see that. So when t is changing, when t is 0, x0, comma, I get the point x0, comma, y0 inside. So I'm just seeing f of this point. When t is moving, when t is increasing, I'm moving away from x0, y0 with speed a, comma, b. So that is with speed u. So here I'm moving away from. I'm looking at values of f while the input of f is moving away from x0, y0 with velocity a, comma, b, with velocity u. Then I'm seeing what's the rate of change of f when I do that. So that's our definition of directional derivative. So this is pretty important. So let me just give the name here. So directional, rather, yeah, let me just say directional derivative. Directional derivative. Okay, so a few remarks. So first, as I mentioned before, this derivative does the thing we were talking about here on this side. So d u hat f of x0, y0 is, or let me just omit the point where I'm evaluating it. This is the slope of the slice of the graph, so this red slice, slope of the slice of the graph by a plane parallel to u. Okay, and the other observation is that we don't have to compute. So this definition with this derivative and plugging in two functions of t in the input the inputs for f in place of x and y. So this complicated definition is the way we think about this, but there is an easy way to compute these derivatives using the chain rule. So let's do that once and for all. So this is this directional derivative is df dt, right? So x and y are depending on a variable t here inside, and f depends on x and y. So when we differentiate f with respect to t by the chain rule, this is, so here it's chain rule. I get the x partial of f times dx dt. So here's x, dx dt. In this case, it's going to be a, so we'll call this a, plus df sub y times dy dt, which in the present case, so y is y0 plus b times t, and so dy dt is just b. So you see, I get an expression, so a sum of two products. This is really a dot product between the gradient of f and the vector with components a and b. We called this vector u before. So in summary, the directional derivative is just the dot product of the gradient vector with the desired direction. But the point is, it's telling us how fast f changes when the input is changing with velocity u in the direction of this vector u with velocity 1, with speed 1. Okay, let's try to bring this down to earth. So for example, so the derivative of f in the I direction, this is the dot product of the gradient with the I direction. Now the gradient, recall, has components f sub x, f sub y. So this is just f sub x, right? Just the x partial of f. So the derivative of f in the I direction is the x partial. The derivative of f in the y direction is the y partial, by a very similar argument. And if you have different directions, you'll get different numbers, which will be combinations of the x and y partials, right? If I have another direction, and that direction is a linear, superposition of I. So if u is a comma b, that means that u is a times I plus b times j. And then the derivative of f in the u direction is going to be a times the derivative of f in the I direction plus b times the derivative of f in the j direction. So so this expresses a nice linearity in the derivative with respect to the direction in which we take it. Okay. So let's move on now to the interpretation. So with this notion of directional derivative at hand, let's move on. Let's go back to the gradient vector and reinterpret it. So let's look at the meaning of the gradient. Okay, so we look at the directional derivative of f, at a directional derivative of f, and we've just seen that this is the gradient of f multiplied by dot product the direction. So if we can draw it, we can certainly draw this, right? So let me just say that f is this vector up here, and that u is the unit vector is down here. And we now want to understand the gradient geometrically. So let's expand this dot product. Let's think of this dot product in terms of geometry, right? So the key here is that there's an angle between the gradient and u, and we've seen that when we do the dot product of two vectors, we can express this in terms of the cosine of this angle theta. So you get the length of f times the length of u times cosine theta. Okay, now here's something. So u is a unit vector, so this is just, its length is just equal to 1. So the directional derivative is going to be the length of the gradient vector times a number, this cosine, a number between -1 and 1. So here's our conclusion. So the derivative is maximum possible. So this derivative is maximum. So in a non-negative number. So this derivative is maximum, and in a non-negative number when theta. So you tell me. So when is this maximum? Well, this product, this number times the cosine, is the maximum it can be when the cosine is 1. So that is when theta is 0. It's minimum. So in this case, it's going to be a non-positive number when theta is when the cosine is -1. That is when theta is 180 degrees or pi radians. And it's going to be 0 when theta is pi over 2. Okay, so you see so the directional, so if I want f to change, to increase as fast as it possibly can, I want to change. So let's say I look at a particular. I'm somewhere in the xy plane, and I want to increase the function f. Maybe f is profit. So if I want to and I'm at a particular point of the xy plane, so if I want to increase f as fast as possible, I want to move in a direction u where this derivative in that direction is the maximum possible. So in that case, so that means I want to choose my direction, making this angle theta, this cosine, to be 1. So I want this angle theta to be 0. In other words, if I want to increase f as fast as possible, I want u to be in the same direction as the gradient. I want to move in the direction of the gradient. Right, to increase f as fast as possible, I want to move in the direction of the gradient. Now, if I want to, let's say f, instead of being profit, was something bad, like an error, a measure of error. And this relates to to very important applications in machine learning. If you want to decrease, if you're somewhere in the xy plane, or in machine learning you'd have more than just 2 parameters, but way more in fact. But the principle is the same. Let's take the situation we're looking at right here. Let's say we have an error that depends on x and y, and we want to change x and y a little bit, little by little, to move away from that error, to minimize the error. So in that case, I want my function, my error, to decrease as fast as it possibly can. So I want u to be such that this cosine is -1. I want u to be, so the angle should be pi. So this means that f should be pointing in one direction, the gradient should be pointing in one direction, u should be minus, in the direction of minus the gradient. So if I move in the direction of minus the gradient, if u is the direction of minus the gradient, then my function will decrease as fast as it possibly can. And finally, if theta is equal to pi over 2, so if u is perpendicular to the gradient, then my function, the derivative will be 0. So my function won't be changing to a first order approximation. Right? Let's look back at the picture at the beginning of the lecture. So I'm saying that if I move in, so here this picture is in 3D, right? But what that is saying is that if I move in a direction that's perpendicular to the gradient, then the value of f won't change to a first order approximation. Now, if you think about this, this is certainly compatible with the theorem from the beginning of the lecture, because that theorem was telling me that if I move inside a level surface, right, if for a vector tangent, so the level surface is a set of points where the value of the f does not change. So if I move in a direction tangent to this to the level surface, the derivative won't change. I mean, the two things are maybe I'm not making this point very well, but the two things are certainly closely related, right? If I'm moving in a direction perpendicular to the gradient, that would be a direction tangent to the level surface, then the function won't be changing to a first order approximation. Okay, so this is what I had to say about the gradient vector and directional derivatives. Now we're going to move on to vector fields. So we're going to be dealing with vector fields in 2D and in 3D. So vector fields in the plane and vector fields in three-dimensional space. So in 2D, our vector field, so we'll get a vector for each point in the plane, and the vector will be a two-dimensional vector. We'll have two components. So for each point x, y in the plane, I'm going to get a vector with two components. The components can depend on, will in general depend on the point, and they can depend, they don't have to be related at all. So normally I'll call, when in 2D, I'll call the first component P. The first component of the vector you get at a point x, y is going to be P of xy, and the second component is going to be Q of xy. And in 3D, we get a vector for each point. A vector field is an assignment of a three-dimensional vector for each point in three-dimensional space. So it's a vector-valued function of three variables. So it'll have three components. I'll write, so the first will be P of xyz, second will be Q of xyz, and the third will be R of xyz. So it'll be useful. So in the future, we'll sometimes denote our vector fields by the notation with I and J notation. So the vector field f is the function p multiplied by the constant vector I plus the function q multiplied by the constant vector j. Similarly, in 3D, the vector field f is p times I plus q times j plus r times k. And here I've omitted the inputs for p, q, and r. Okay, so the point is, for each point in the plane, you get an arrow, and the way we tend to draw this, tend to depict vector fields, is just by, you start with, so say we want to draw a 2D vector field. You draw the plane, and then you pick a bunch of sample points in the plane. So you pick a point, and you evaluate f, you see what vector you get. You just draw that vector. But instead of drawing that vector starting from the origin, you draw the vector with its tail at the point x, y that you were evaluating the vector, at which you're evaluating the vector field. Right, so because otherwise, if we were drawing f of xy always with its tail at the origin, you'd get different, you'd get a bunch of points, a bunch of vectors emanating from the origin. It'd be hard to distinguish them. So it's easier. So it becomes easier to parse and understand the picture if you draw the tail of f of xy being at the point x, y. So we see vector fields all the time. So for example, so first of all, we've already seen a vector field. The gradient of a function is a vector field. The gradient of a function of x and y has components x partial, y partial, right? So p is f sub x and q is f sub y, and you get a different gradient. You get a different vector depending on where you evaluate the gradient, on where you evaluate the partials. And the gradient of a function of x, y, and z will be a three-dimensional vector field. So this is an important class of vector fields. Another important class comes from, so the other important classes come from physics. So for example, if you start, so in fluid mechanics, if you're interested, if you're studying a fluid, it's useful. It's one of the ways you can describe the fluid is by, saying the fluid is occupying this region of space, and at each point in the region, you describe the velocity of the fluid at that point, right? But then at different parts, the fluid maybe here maybe the movement is going, the fluid is flowing, and material is flowing sort of along the trajectory such as the one I'm doing with my hands, and then you see that the velocity is pointing down, and then points to the right, and then up, right? So it can depend. So a big important example of vector fields comes from fluid mechanics, the velocity field of the fluid. The other important example is force fields, or things very close to force fields. For example, electric fields tell you force per unit charge. It's almost, so you get a force vector divided per unit charge. You get an amount of force per unit charge at each point in space. Or magnetic fields, which are similar, but for a different sort of interaction. And of course, gravitational forces. Okay, so a cool example of a 2D vector field would be, for example, a map of Washington State, or maybe if you look at a smaller scope, a map of Seattle, and then at each point on the ground, you just measure, you see which way the wind is blowing and how fast it is blowing, and then you'll see that, and then you put an arrow at that point on the ground. I mean, you draw an arrow at that point on the ground with that velocity, wind velocity, and speed. And then if you look from high up, you'll see a sea of arrows, a field of arrows covering the map. That would be, so fluid velocity in this case, the fluid is the air, gives you a nice visual concrete vector field. And an interesting thing is, so in this class we're headed towards, we'll learn how to differentiate and to integrate vector fields. So we're really starting the second half of our class. Of this course, and so what we're going to be doing is we'll be doing calculus with these things. So we'll learn, for example, to differentiate so two kinds of derivatives that we could take of a vector field: the divergence and the curl. So these are combinations of the partials. So particular combination of the partials of P and Q in 2D of the components of the vector field in general. And these derivatives, they have suggestive names, divergence and curl, because in the fluid velocity case, the divergence, which is one of the two derivatives in the fluid velocity case, it's telling you how much the fluid is expanding at each point in its extension in the region it occupies, and the curl tells you how fast the fluid is rotating at each point. So one other thing we'll learn how to integrate vector fields along curves and surfaces, and we'll learn how to interpret that too and relate to these derivatives. So at the end of the course, I'll give you big theorems, which tell you what happens when you integrate the derivative of a vector field over a curve and over a surface. Okay, so let's get started. Do some more concrete examples. So here's a simple example of a vector field. So F it's always the vector 2i plus j, right? 2i plus j means you go 2 to the right, 2 units to the right, and 1 unit up. And it's always the same vector at each point in space, because the right-hand side doesn't depend on x and y. So you get a picture like the one you see. Here's another example. So here the vector field does not depend on y. So you see that if I know what the vector looks like, vector field, what vector I get at a particular point x comma y, for all other points with the same x coordinate, I get the same arrow. I get the same vector. So here, this one is not too hard to analyze. You see that where x is non-negative, I'm going to get a positive multiple of I, and that the larger x is, the larger this multiple. So I get a larger arrow. And if x is negative, then I'm pointing the other way. Here's another example. So this one, so I'm calling it R instead of F, right? R, so R is a fine name for a vector field 2. So this R, so the x component at a point x is x, and the y component at a point y is y. In other words, R is if I R at a particular point x comma y is just the position vector of that point, right? So if I look at this point, its position vector is the same. I just transformed the point into an arrow, but then I redraw that same arrow with its tail at the point. And if I do this at all points in the plane, I get something that emanates from the origin like this. And finally, one last explicit example that's still understandable is this one. So here I drew this rotating pattern. So the vector field f is minus y comma x, right? So the I component is minus y, the j component is x. So this I claim is the position vector xi plus yj, but rotated by 90 degrees to the left. So let's see why this angle here is 90 degrees. Well, if you take this x, so if you take the vector, let me write this in component notation. I sometimes find it easier to pronounce. So if I take x comma y, and then, so I claim that this is 90 degrees, right? This is same as saying that the cosine of the angle between the two vectors is 0. Or in other words, that the dot product of the two vectors is 0, because the dot product is the product of the lengths. So here are two non-zero numbers times the cosine. And the cosine is 0, the dot product is 0 if and only if the cosine is 0, if and only if the vectors are perpendicular. So in this case, you can see that if I do the dot product, minus y comma x with x comma y, I get minus y times x plus x times y, cancels, I get a 0 for every single point in the plane. So f is always pointing at 90 degrees angle with the position vector. And also notice that f, the length of f, is the same as the length of the position vector, right? So the length here at each point, at a point x comma y, the length of f is y minus y squared minus y, everything squared, plus x squared. That's the same as x squared plus y squared. So these vectors have the same length. And the last thing to check, to see that it's rotated to the left, you just plug in, rather than to the right, you just plug in a few values. For example, if x is 1 and y is 0, then f is going to be minus 0 comma 1, which points up. Or for example, if x and y are both 1, so I'm in this diagonal, then f is going to be minus 1 comma 1. So it'll have a negative component, and the I will have a negative component, and the j component will be positive, and so on. So this is rotating to the left. So next up, I'd like to do an example relating to so I've discussed the applications to physics. The big ones are fluid dynamics and force fields and things like that. Let me just write down a few force fields. So first, let's start with gravity. I'm going to write these down, and then you can use them and understand them in your homework. So let's say we have a big mass at the origin. So I'll call this big mass capital M. And I have a small mass, a test mass, little m, some distance from the origin. And I'll call this is going to be useful later. We'll call this vector that points from capital M to little m R, right? So this has components x, y, z. It's just the position of the test mass. So the force, we'll look at the force of the big mass on the test mass. So this is gravitational force. So we know that the absolute value of this force, so the magnitude of the force is just a constant, so Newton's constant G times the product of the two masses divided by the distance of the two vectors, so R squared, length of R squared. Okay, now what about the, so this is just the magnitude of the force, but we also know that the force is attractive, right? So it points, so it's going to be some number, so the force is going to be this number, GMM over length of R squared times a unit vector which tells us the direction of the force. So in this case, the unit vector. This force is attractive. It points little m towards capital M. So the distance is opposite to the direction is opposite to R. And I'm going to divide this direction by the length of R, so I get a unit vector as my direction. So this way, this part has length 1. This part has the correct length. So this whole thing. So this is length 1, so the whole thing has the length I want, and it points toward the origin, as it should, right, towards capital M. So as a result, you get a funny cube in the denominator. So I have all these constants, G, capital M, little m, multiplied by, in fact, there's even a minus in front of everything. I'll count that as a constant as well. But then and then this is multiplied by a vector that depends on the position. So that's R divided by R cubed. Right, so this really, if we unpack it all, this is x, y, z divided by root of x squared plus y squared plus z squared.